Hello guys, welcome back to another episode of Talks Riders. In this video, we want to have a mini project in FreeFEM in which we develop a transient heat transfer model using parallel computing techniques. Let's go for it. So in the previous episodes of Talks Riders, we talked about FreeFEM and parallel computing in two different series. I want to quickly show you where we talked about them. So I go directly to the YouTube channel and playlists. So we had a playlist on FreeFEM, and in this playlist, I open it. We had a couple of videos in the end about solvers in PETSc, parallel computing, and mesh partitioning. And I will use the techniques that we'll learn in these three videos in order to parallelize a model we developed in this series, Introduction to Finite Element Modeling, and the heat transfer or diffusion problem inside this helix shape geometry. And in the video number 4, we developed that inside FreeFEM. So I will use this code. I don't go through the weak formulation and all the variational implementation anymore. If you don't know what I'm doing here, you need to go back to this video as well as the other 3 videos that I showed you in order to grab the essential concepts of parallel computing and weak formulation. So I go to the GitHub account of Talks Riders and inside the repository. Here is the FreeFEM intro. So as I said, I will use the techniques in the domain decomposition, and in order to do that, I will go through this one, Poisson parallel. I will use the techniques that I describe here. So I open it inside a new tab, and so this is the code. And the one that we are going to solve is very similar to this one, but it will be a time-dependent transient problem. And the code itself that we are actually going to parallelize in this video is this one. So I scroll down, and inside of FreeFEM, Finite Element Intro and episode 4, as I showed you, this is a code that we need a mesh. And the mesh was already produced in previous, videos. So here, these videos, I described how to create a mesh. And then in video number 4, we solved that inside FreeFEM. And for the rest of the videos, we solved the same problem in different tools. Same tools that you can use, weak formulation, and tools that you use a graphical user interface, and those kind of things. So to episode 4, finite element intro, and a transient heat EDP is this FreeFEM file, and the helix mesh is a 3D geometry that we're in inside a program, and then we perform the simulation on it. So I have downloaded the file here. So this is it. I open it inside the text editor. So this is the code. As you can see, there are some stuff here that we have the variables, the time, and the diffusion coefficient, and all these things. We read the mesh. Now, as I said, I don't want to go through this. This is a weak formulation. This is a finite element space. And then we have a loop here, for loop, that iterates through all the time steps that are needed, and then saves the files inside, a directory and a VTU file, set of VTU files. So I run this file in order to have some references, that we want to compare if we have correct parallelization, because this is a code that we want to work on and make it parallel. So I run it. Probably if we face an error about a VTK file. That's true, because we haven't had the output directory here. The FreeFEM doesn't create it automatically. So make directory output, and then I run a file. Now it should start to work. And I have a set of files. Each 3 steps, I write the output to VTK files, in this case VTU, and then we have these files here. So I interrupt the simulation, and then I open ParaView to see what we have here. inside the output directory, and yeah, this is the simulation results. As you can see, the mesh is quite coarse, which is not suitable for parallel like computing in this video, but that's okay. You know, you can make it fine yourself. You can refine it, let's say. So I changed the color map, and then this is the diffusion that, as you can see, is quite fast. Yeah, and then because we have a high temperature here on this side and a low temperature on this side, as you can see, plus 20 and minus 20 being applied on, you know, here inside the weak formulation, depending on the region labels of those regions. You know, as I said, you can go through the playlist and then you can see how it is developed. So now we want to make this code parallel, and in order to do that, as I said, so I close preview, and then I will make a new, I copy this, so transient heat, I will copy that as now for example, parallel transient heat. So yeah, now I open this file and I want to make it parallel. And in order to do that, as I said, I will refer to this file. I will use the techniques that I showed you here. So as you can see, we need to load a PETSc plugin and this macro, that is, this input file, the macro DDM for domain decomposition. And these are described in video number 11 and video number 9 of the FreeFEM series. And you know, we don't need these things anymore for Mesh 3D and IOVTK. These are things that are automatically loaded by the plugin and also this macro file. And for the dimension, we have dimension 3. This is a 3D problem, and the rest is this will run in parallel. So as we discussed before, you should always remember that this is a parallel code, and all these codes will run in different instances, in different nodes of the same program. And we are okay. We need all these things in all the nodes, let's say. For mesh, you know, I will come back to this. This is quite okay because we need a mesh in all the instances of the program. But one thing that can be quite efficient, especially if you need to do some geometry pre-processing inside FreeFEM, is that you can run it inside like only the processor number 0, so like MPI rank 0, and then broadcast it through all the other nodes. So this is also something that we discussed before. I won't do this at this moment, but in the end of the video I will show you how to do that again. And here we define the finite element space. That's a first order finite element, so this is fine, and u equals u0, which is defined 0 here. And then here is one of the parts that we need to change. As you can see here, and we discussed before, you need to do, you know, the formulation of the weak form inside a varif statement instead of the problem or solve keywords inside FreeFEM. This is something we need to change here. I change it, and depending on this is really important. This is something we have discussed in one of the episodes of the FreeFEM series. I will show you which one. I think that would be easier if I show you. So inside the FreeFEM series, there is, I think, number 4. Yeah, number 4 and 5. Most important, number 5. We actually discussed the differences between different forms that you can implement the weak formulation inside FreeFEM. And varif is the one I said inside, and you know, later on for high performance computing, this is really important that you actually consider using this one. And here, because we will assemble the right hand side and left hand side using the same statement, that is this one, we need to take into account that this is something that we will assemble the right hand side, and as a result I change it to plus instead of minus, because in the problem kind of implementation with the problem keyword, we move everything to the right hand side or left hand side in this case, and then we solve it. But in this case, in our problem here, I move the right hand side back to right hand side, and as a result I need to change the sign here. So please refer to those videos if it is still unclear to you that why I did this. And then we need to define, the mesh partitioning, and also two variables or arrays and metrics that we use to store the A and B when we want to solve something like this, AX equals B. And in this case, it is U that we want to solve for. So I assemble the A and B, and for assembling A, I will also decompose the mesh. This is what FreeFEM does for us, actually, this PETSc plugin. So this is a code that I can use to create the A matrix, and I will use a preconditioner, like in this case as a algebraic multi-grid AMG from the Hebrew package. And the finite element space should match with the one that we want to use, and then this create math function or macro will decompose the mesh for us. And then for B, it's also very important, and then we make it like an array. It's a one-dimensional array, and the size should match with the number of degrees of freedom that we have in our finite element space. So this is the way that I assemble A and B. Of course, this is the way that I created. Later on, inside the loop, I will assemble it. And then for the rest, there is nothing special that we want to do. As you can see here, this is the way that we can assemble it using the space P1 for A, and 0, and the space P1 for B. So I'll do it here. So instead of the thermic that calls the problem, I say A equals like thermic, so the same thing, but instead with the space P1 and space P1 for the test and trial functions. And for the B, I would say thermic 0, A space P1. So this is A and B, and then we need to solve. We have already defined U, so we don't need to define it like this for solution. We already have U here. That keeps the problem, like the solution of the problem, and then it also assigns it for the previous, like the time steps U old, so that it can be used here for discretizing the temporal term. So this is the way that we can define it. As you can see, this is the way that FreeFEM calls the PETSc solvers. We have discussed this before, and then the solution will be actually generated, or the equations will be solved. And then we have the same thing here. As you can see, every 3 steps we solve it. We store the problem, the solution to the disk. And for that, we don't need this decounter anymore, because the PETSc plugin inside FreeFEM takes care of that. There is something very important here, but for now I will run the code, and then we will discuss it. So this is really like the skeleton, very important skeleton that is like the basis for all the parallel problems inside FreeFEM, and this is for a time-dependent one. And now we are ready to run it actually. So as we discussed, we need to call MPI run. In this case, I just run with 3 cores, because as I said, the mesh is quite coarse, and more than this probably will also most likely would increase the runtime actually. So FreeFEM ++ MPI, and then the name of the file, and I would say v0. Let's see what happens. Probably the first error we get is for the folder, but apparently it's, oh sorry, I wanted to, so it is now writing this inside this one, so I don't want to do that. I want to like write it in parallel, so output parallel, and yeah, this is really important that I make the directory inside like the output parallel. So now there shouldn't be any problem, because I don't want to write it there. I want to have the output being written in a separate file, separate directory, sorry. So now the code is running, as you can see, but I don't see anything here. That's something that I will add later. But it's going on, solving things, but it writes things on a same kind of the same files. And output tree, this is a typical, like as we discussed before, typical output for parallel runs inside FreeFEM. And then we have like the 4 different time steps depending on the number of cores, we will have VTU files, and a PVD is kind of a file that groups or wraps these files into one file that can be loaded inside ParaView. So if I add here, I say that if MPI rank is 0, so say that, for example, we are solving, let's say, I don't know, iteration or time step number count. Sorry. So this is what I say here, and then it should tell us that which iteration at this moment is being solved. As you can see, it's actually progressing. It's quite fast, but still I have only these 3 files here. And the reason is here I'm saving it's on a same file, so indexing is not a problem. But say WDK has a kind of an argument here that says, should I append to the previous results or it should be overwritten? So this is something very funny. We can use like a kind of trinary operator here, this trinary operating for if else. So I say the condition here, so this is the condition, this is if it is true, and this is if it is false. So this is a trinary kind of operation. I say count, it means that if count is 0 or is not 0, so for the case that it is like for iterations that are not the first iteration, this is true. So I say for those iterations you should append it, and if it is false, means that count is 0 because I increase the count at the end of the loop, then append is false. So for the first iteration, for the first time step, you should overwrite the results, most importantly this output 3, which is the wrapper for the rest of the files. And if it is not the 0, so the simulation is going on, the append should be true, meaning that you should append the previous results to this. And it should solve the problem. Let's see what happens. Yeah, as you can see now we have the files being written here and the simulation is progressing. So I stop it here, and now we should be able to have like the simulation files from this PVD file. So I open a PVD file here, and if I should like plot the WDK composite index, you can see that we have or block colors, it doesn't matter. You can see that we have 3 blocks, and it is also here. It can be visualized here that we have 3 blocks because this is mesh partitioning. And then if I plot the scalar 1 here, it will be like this. So let's see. Yeah, apparently it's not very, I don't like the results. We will go through it to see what happened here. So let's see first. No, it doesn't work. So there is something wrong here. This is actually interesting to also debug it a little bit to see that what is wrong inside this code. So I close ParaView and then I go back. I have also a couple of guesses here that what a problem can be. Well, let's go through the code, step by step and see where the problem is coming from. The thing is, when we decompose a mesh into some subpartitions in FreeFEM, there is a problem that is actually related to mapping the variables or functions or state variables that are defined on the global mesh into the local mesh. So as you can see here, so this is my first guess that we can try to see if that's the problem here. I didn't do that because U0 is 0 here, so I thought that maybe that's not a problem, but maybe it is. That U is currently defined on the global mesh, and later on when we decompose the mesh, we never said that map it into the local ones. And later on we use the local things and, we just assemble everything in the post-processing software. So let me, before starting the loop, before doing things, let me map U from the global U, which is this one, into the local one. And U equals U is a kind of notation for calling the interpolator inside FreeFEM, to map from the global one that was defined before into the local one that exists after decomposing the mesh. So let's see if it solves the problem. So I run it again, and it runs for a couple of iterations. I guess that it should be the problem, but let's see. So I run ParaView, and here I have like the PVD file, apply, and yeah, so we have 3 blocks and the scalar. Yeah, so that was actually the problem. So we needed to call the interpolator to map U from the global one into the local one. So now it should work very nice inside Parallel. And if we had like a finer mesh, as I told you, it could be like you could see bigger difference between a serial run and a parallel. So this is actually the way that we parallelize the code, and as I promised in the beginning of the video, I will also show you how to, the more efficient way of dealing with this. So this is not a case here, but in like real applications, when you also do some geometry pre-processing, it can be easier if you read the mesh inside the rank 1. So you don't want to deal, you don't want to engage other ranks, other nodes, other instances of a program in geometry pre-processing or formatting or, remeshing, all these things. And when you are done with that, in this case, this is just a load, but when you are done with that, you can broadcast the mesh. So we can say broadcast from processor 0, because it's processor 0 that does these kind of things, and then the name of the variable that we wanna broadcast into, to the other processes. So in this case, that is just the mesh number 0 that does, reading the mesh, and it sends it to the other processors, and then it starts to run. So yeah, that was the mini project that I wanted to discuss in this video. I hope you find it useful, and it helps you to, make your codes parallel. If you have any serial code in FreeFEM, any kind of model, this is the way that you can, do it by calling the PETSc and some input files, and then some really minor changes inside the code. Yeah. That's it. See you in next videos. Bye.